Swayam Prabha. Digital India. Educated India.
So, in the last lecture, I have told you something about the alternative charge material in the electric arc furnace. There I said three different types of charge materials are there in the practice. One is the hot metal, another is the directly reduced iron or sponge iron or HBI, and third I have said about the iron carbide. I have also mentioned that proportion of hot metal is not unlimited, because electric arc furnace traditionally was developed for melting unit. If we charge hot metal, since hot metal contains varying amount of impurities starting from carbon, silicon, manganese, phosphorus. So, depending on the proportion of hot metal in the mix, one has to carry out refining. That is, one has to carry out oxidation, one has to supply oxygen, and hence the refining time may increase with the proportion of increase in the hot metal, and hence step to step time may increase with the more proportion of hot metal in the feed. So, taking into all these aspects under consideration, a 30% hot metal is considered to be an optimum amount for maintaining the reasonable tap to tap time comparable with the 100% scrap practice. Increasing amount of hot metal, though it can be used, but it will increase tap to tap time, and increase in tap to tap time will be associated with all disadvantages like increased refractory wear, increased electrode consumption, then increased electrical power consumption, and so on and so forth. Now, the another charge material is the directly reduced iron, and that is what I will be telling you something about directly reduced iron today. In fact, this directly reduced iron is produced by reduction of iron ore. It is produced by reduction of iron ore either with coal or with gaseous reducing agent or with gaseous reducing agent. So, the temperature in the production of DRI rarely exceeds 1000 to 1100 degrees Celsius. That means, we are not melting any component of the iron ore, simply the oxygen content of iron oxide is getting removed. So, whatever impurities will be in the iron ore, the same will be transferred into the DRI. So, essentially DRI or HBI both are the same thing. DRI, it contains free iron plus oxygen combined with iron, plus carbon which is left plus gangue minerals plus gangue minerals, and these gangue minerals could be SiO2, could be Al2O3, could be TiO2, etc. That means, whatever present in the iron ore is transferred into the DRI, because no melting is being done, the reduction is carried out in solid state. Therefore, it is important to characterize DRI. Characterize means what is the quality of DRI that is being used in the electric arc furnace as a substitute for scrap. So, the quality of DRI, first important parameter is percent metallization. And this percent metallization, that is equal to free iron upon total iron into 100. That is the one important characteristic of DRI before it is considered to be used as a substitute of scrap in electric arc furnace. The important thing to know for an operator or for the person who will be using DRI is what is the percentage metallization, because any amount of oxygen that is left with iron in DRI, it will be removed in the electric arc furnace. For example, if we have say 90% metallization, then 90% is the free iron and 10% iron is in the form of FeO or Fe2O3 or Fe3O4, whatever the form may be. So, it is in that reference the percentage metallization is an important component of DRI. Second important thing is that how oxygen is present, that is either oxygen is present as FeO or Fe2O3 or Fe3O4. So, now this is also important, that is in which form oxygen is present in combining with the iron, FeO, Fe2O3 or Fe3O4, because any oxygen which is with the gangue mineral, it cannot be removed and it is not removed. That point should be clear. What removal of oxygen we are talking about is the removal of oxygen from Fe2O3. So, if we say 90% metallization, that means 90% is the free iron and rest iron is either in the form of FeO or in the form of Fe2O3 or in the form of Fe3O4. Now, it is important to know in which form iron is one, and because ultimately when this DRI will be charged in the electric arc furnace, we will like to reduce oxygen and get iron back as a yield. So, if the iron is present as Fe2O3 or Fe3O4, then higher amount of energy is required, but if it is present in the form of FeO, again higher heat load is required, because FeO plus C is an endothermic reaction. Now, let us calculate, say, what is the amount of oxygen that is present in DRI. So, let us assume that oxygen is present in the form of FeO. Oxygen in DRI is present in form of FeO. So, we can calculate now, say percentage FeO, that will be equal to percent iron total minus percent iron metallic into 72 by 56. So, therefore, oxygen in percent, that will be equal to 0.285 into percent FeO, because 16 kg oxygen is present in 72 kg of FeO. From that you can get oxygen percent is equal to this. Now, this is the oxygen present in the form of FeO. Now, this oxygen removal also requires carbon. So, therefore, carbon in DRI is important. Carbon in DRI is important. Carbon in DRI is important because ultimately this FeO will react with carbon and will get Fe plus CO, and this reaction requires carbon. So, if we look this reaction, then what we see is that 16 kg oxygen, it requires 12 kg carbon. So, 1 kg oxygen requires 0.75 kg carbon. So, what I wanted to say from here is that if carbon content in DRI is maintained at 0.75 ratio to the oxygen of FeO, then carbon will react stoichiometrically with FeO during electric arc furnace operation. That means what? If it reacts stoichiometrically, good, it will reduce FeO and you will get the iron. It is endothermic reaction, no heat will be produced. That is one case. Now, if carbon content in DRI is more than the stoichiometric amount, that means if carbon content in DRI is greater than stoichiometric amount, in greater than stoichiometric amount, what does this mean? There will be extra carbon left in DRI. So, to remove extra carbon, I have to inject oxygen, and C plus O is equal to CO. So, it will generate a large amount of heat. So, that is what is important. So, what is important is that carbon content in DRI that can be taken care of during the production of DRI, it should be greater than the stoichiometric amount of carbon required to reduce FeO to iron. So, if the carbon content is DRI is greater than the stoichiometric amount, then extra oxygen has to be injected, and on account of extra oxygen injection, the reaction between carbon and oxygen will be producing carbon monoxide. So, there are two advantages. One, this is slightly exothermic reaction, it will produce the amount of heat, and second, the carbon monoxide bubble which has been formed, they will also help in foaming of the slag. So, this particular carbon content in DRI is greater than the stoichiometric amount, will need extra amount of oxygen to be supplied, will need extra amount of oxygen is to be supplied, and that helps in two ways. One way is you produce heat, through C plus O is equal to CO reaction. Second, the CO bubble, it induces foaming in the slag. So, these are the advantages of say having carbon content in DRI greater than stoichiometric amount. So, what this discussion leads to, that quality of DRI, there are certain important things. First important is that metallization, and second important thing is the carbon content in DRI. Now, remember at this point of time when I am talking of the oxygen content of DRI, then I only mean that oxygen which is present with iron, because no oxygen which is present in the gangue mineral is removed in the process of manufacture of DRI. This should be very clear. So, now let us see the effect of metallization. So, take a case, for example, consider 100 kg of ore. Consider 100 kg iron ore, say 56% iron. So, it has around 80% Fe2O3 and 20% gangue, 80 kg Fe2O3 and 20 kg gangue. So, I carry out now metallization. I produce now DRI from this particular iron ore, then I calculate some kg iron, then kg iron which is combined with FeO and kg gangue. So, if the metallization for example is 80%, then 45 kg is iron, 11 kg iron is present as FeO and gangue will of course will be 20 kg. If I go for 85% metallization, then I have 48 kg iron, 8 kg Fe2FeO and well of course gangue will remain the same. Similarly, 90% metallization and 95% metallization, here kg free iron will be 50 and kg free iron will be 53 kg, here it is 6, here it is 3, here it is 20, here is 20, because whatever amount of gangue is there, it will transfer to DRI. So, in the amount of gangue nothing will change. So, what is important to see from here? If I increase degree of metallization, say increase in degree of metallization, what it is doing? It is increasing the free iron that is being charged with the DRI. That is, first it will do increase in free iron, increase in free iron. It is good because it will contribute to the productivity directly. Second, it is decreasing the iron which is combined as FeO. That is also good because less amount of energy would be required to reduce FeO by carbon to Fe plus CO. As a result, what will happen? Less heat will be required during processing, less heat will be required. Productivity will be more. So, if I want to illustrate schematically, if I take here productivity and plot it against percentage metallization, I go from 80% to somewhere as 95%, then productivity will increase as the degree of metallization increases 80% to 95%. But well, in order to produce a high percent metallization, the investment cost is also important because it takes sufficient time and sufficient thermal energy to produce highly metallized product, that is a very high quality product. And besides that point, from our argument sake, if we increase the metallization in our DRI, then our productivity is increased. Now, let us see the another effect. For example, for a constant degree of metallization, if we increase the proportion of sponge iron, that is, I take 90% scrap, 10% sponge iron, 70% scrap, 30% sponge iron, 60% scrap, 40% sponge iron. In that I vary the proportion, then let me see what effects it does on the various constituents. So, what I am doing now, I am taking now say 100 kg sponge iron, I am taking now 100 kg sponge iron or DRI of 90% metallization of 90% metallization. Now, just a background calculation, you require around 132 kg of iron ore of 80% Fe2O3 and 20% gangue. So, if you want to calculate again what is the effect of changing the proportion of DRI in the feed on free iron, Fe to FeO and the gangue, then you have to perform the calculation by considering how much amount of iron ore is required, how much amount of iron it has and how much amount of gangue it has. I have done this calculation and I am presenting here. So, I am taking a case, say scrap, then I take sponge iron, then I take sponge iron, then I take free iron, then I take iron which is present as FeO and the gangue content. So, if I take now 90% scrap, 10% sponge iron 10 kg, free iron will be 6.6 kg, 0.8 kg and 2.6 kg. If I take now 70% scrap, 30% sponge iron, I have 19.8 kg free iron, 2.4 kg as iron is FeO and 7.8 kg in the gangue. If I take 60% scrap, then 40% sponge iron, 26.4 kg is the free iron, 3.2 kg as the iron is FeO and 10.4 kg gangue. If I take now 50% scrap and 50% sponge iron, 33 kg will be free iron, 4 kg will be FeFeO and 13 kg present as a gangue. What this calculation indicates? So, increase in proportion of sponge iron, talking of the same productivity, I have taken the same productivity. So, increase in proportion of sponge iron, what is doing? First, free iron is increasing, okay, this is good, no problem. Second effect, iron which is present as FeO is also increasing, It is not good. Why it is not good? Because FeO plus C is an endothermic reaction. So, more amount of heat you require to reduce FeO to iron, because you do not want to lose FeO in the slag. You have an option, you can lose FeO also in the slag, but you do not want to do it because it contains iron. So, Fe as FeO is also increasing, as you see FeFeO from 0.8 kg it goes to 4 kg. So, third thing is that gangue content is also increasing. Gangue content is increasing in the mix that you have prepared. That means, if you take 50% scrap and 50% sponge iron, 13 kg is the gangue. If you take 90% scrap, is 10% sponge iron, 2.6 kg is the gangue material. Gangue content is increasing means what? More slag volume. More slag volume means what? More heat load. Because you have to supply extra amount of energy. So, what is the consequence? What is the consequence of it? What is the consequence of it? The consequence of it, one, increase in the proportion of sponge iron in the feed. It is increasing Fe which is combined with FeO as well as the gangue. So, therefore, the tape to tape time will be influenced, For a small proportion of sponge iron, say 10% or let us say between 20 and 30%, the tape to tape time may decrease, because that extra load is not that much, but beyond that the load will be too much and tape to tape time will also begin to increase instead of decreasing. It appears as if there is an optimum percentage of sponge iron where tape to tape time should also be decreasing. Increase in tape to tape time by increasing the proportion of sponge iron is not very good, because if the tape to tape time increases, electrode consumption will also increase, refractory wear will also increase, and productivity will also be affected. So, these are the some of the calculation that I thought I will illustrate. Now, the next thing is that the charging methods. So, let us see now the charging methods. Charging methods. Say one can have batch charging, that means the DRI is charged in batches. So, batch charging is rather good for small capacity furnaces, For small capacity furnaces say less than 5 tons capacity, and batch charging is also preferred. This batch charging is preferred up to 25 to 30% DRI. Any increasing amount one has to see other method. So, another method is continuous charging. Continuous charging is done for furnaces 10 tons capacity or more than 10 tons capacity. And this continuous charging has certain advantages. So, the advantages of continuous charging, you can think of, you have the roof of the electric arc furnace where 3 electrodes are inserted. Still there is a space on the roof, and that space can be used for charging sponge iron continuously as and when it is required in the electric arc furnace. So, you can think of the advantages, because now you do not need to open the roof for charging as you have to do for batch process of charging. So, the advantage is that first advantage is less power of time, because now you do not need to switch off the power while charging as in case of batch charging. The advantages are there, less power of time. Second, heat losses. Resulting from delays are eliminated. It is obvious also, is it not? Because what you are doing, you are not removing the roof as you did for batch charging. So, whatever the heat losses which were there during charging, it is not there. Delay is also not there, because the process is going on and charging is also going on. So, that way heat losses resulting from delays are eliminated. Third, as a consequence of which, you have lower electrical losses. lower electrical losses. Fourth, overlap of charging and refining. Overlap of charging and refining. What does it mean? That means both charging and refining can be carried out simultaneously, because the process is on, charging is continuous. So, charging and refining are overlapping in each other, that is good. Fifth, say reaction between carbon and FeO of DRI is taking place during the charging of a sponge iron. So, as a result, this reaction produces heat. This reaction produces strong carbon boil, during charging. Now, remember, this reaction between C and FeO, it takes place during charging, and the CO which results, it creates a strong bath agitation in the bath. So, this carbon boil, it improves heat transfer and slag metal mixing. These are the certain advantages associated with continuous charging, and now it is obvious also, now anything which is continuous, all the delays which are associated with the batch, they are eliminated, and hence the advantages are obvious. Now, a little bit about the Indian condition. So, under Indian condition, the power consumption is around 600 kilowatt hour per ton with heavy melting scrap. So, if 40 to 50% of scrap is substituted by sponge iron, then power consumption will go up, say roughly a figure of 10%. Now, this is mainly because you have introduced extra gangue content, you require to remove oxygen of FeO, and because of this the power consumption also increases. Now, in fact, electric furnace can be charged with 100% sponge iron also. Now, this is only possible for ultra high powered furnaces. So, this is about the assessment of DRI as a feed for electric arc furnace. Now, third is use of iron carbide. Use of iron carbide, which is Fe3C. Now, this Fe3C, it contains 6% carbon. The melting point of Fe3C, melting point of Fe3C is 1837 degrees Celsius. It's a very high melting point. It can also be used as an alternative charge material, but certain precautions are to be exercised during charging. First of all, say Fe3C is charged below the slag layer, charge below the slag layer. Why? Because then it can dissolve. So, with this, say Fe3C, it dissolves in slag, it dissolves, and carbon reacts with oxygen. It will give two benefits: one, saving in power, and another benefit is because carbon monoxide is evolving through the charging of Fe3C. So, it will also contribute to foamy slag practice, practice. So, this is about the alternative charge materials. In the future, the proportion of sponge iron, hot metal or Fe3C will increase, and its increase would depend upon what is the quality of scrap available and what is the quality of steel that is desired. So, that is all about the alternative charge material. Now, the next topic that I want to tell you is about stainless steel making. Stainless steel making. Now, some of the manifestation of stainless steel is that the stainless steel denoted by SS, it contains 10 to 30% chromium, contains 10 to 30% chromium. Minimum 10% chromium to maintain corrosion resistance, to maintain corrosion resistance. Second, stainless steel also contains varying amounts of alloying elements, varying amounts of alloying elements like nickel, molybdenum, vanadium, titanium, etc. Now, these alloying elements are added in order to get some special property. Now, certain types of stainless steel, one, austenitic, and this austenitic steel composition, a rough idea I am giving composition: 18% chromium, 8% nickel, carbon may vary from 0.03 to 0.15%. So, remember, the austenitic steel is characterized by low carbon and high chromium. That is important for the lecture which is coming now. Another grade is ferritic. Now, ferritic grade has 12 to 30% chromium, 0.08 to 0.12% carbon, again low carbon, high chromium. Third grade is martensitic. And they have approximately 12.7% chromium. The carbon content, it may go from 0.15 to 0.25, but certain grades have carbon in between 0.6 to 0.95. Another variation is duplex steels. Now, in the duplex one, chromium is around 25%. Then there is still another variety, the precipitation hardening steels. Precipitation hardening steels, and they have say 18 to 20 chromium plus copper, titanium, aluminum plus 8 to 10% nickel. They are highly specialized steel and used for certain specific purposes. Now, say about the production of about production of stainless steel. Electric arc furnace is used for production of stainless steel through melting stainless steel scrap. Hardly refining was required because stainless steel scrap was available of the composition which is required for the product, it was melted, and stainless steel of that particular grade is there. But again, over the years what has happened, shortage of high quality stainless steel scrap, shortage of high quality stainless steel scrap has required to find out alternative charge materials so that the quality of the steel remains as it is required. So, again the problem of having the shortage of high quality stainless steel scrap. So, this required alternative charge material, required alternative charge materials, alternative charge materials. Now, what are these alternative charge material for production of stainless steel? One, carbon steel scrap, carbon steel scrap. Then of course, you have stainless steel scrap, stainless steel scrap. Then in order to meet the chromium content, you have to charge ferrochrome. You have to charge ferrochrome. Now, there are three grades of ferrochrome are available. One grade is low carbon ferrochrome, and this low carbon ferrochrome contains approximately 0.1% carbon. Then we have medium carbon ferrochrome, and this grade contains around 2% carbon. Then third grade we have high carbon ferrochrome, high carbon ferrochrome, and this may have approximately 7% carbon. What is the problem in this? The problem is very simple. You are charging carbon steel scrap, you are having stainless steel scrap, you mix and calculate the amount of chromium is far less. Then you have to add the charge material which contains the chromium. That means ferrochrome is to be produced. You can argue, sir, let us use low carbon ferrochrome, fine. The production of low carbon ferrochrome is very expensive as compared to production of high carbon ferrochrome. If you have read the ferroalloys, production of ferroalloys, you will recall from there that production of low carbon ferrochrome is very expensive as compared to production of high carbon ferrochrome. As a technologist, as a producer of stainless steel from electric arc furnace, you will love or you will like to use medium or high carbon ferrochrome if the technology exists. Otherwise, you have no choice except to produce use low carbon ferrochrome and to see what is the cost of the stainless steel that is coming out of the furnace, because the cost of production of ferrochrome will also be added up in the cost of stainless steel. So, this is the main issue, whether we go for low carbon or high carbon or whatever type of ferrochrome. The another alloying element is a primary nickel you also require to add, because certain grades which require nickel, you have to add nickel. So, with this now what has become important now for production of stainless steel is that refining became essential to produce stainless steel in electric arc furnace. As you noted, the different grades of stainless steel require carbon very low. So, if you use high carbon or if you use carbon steel scrap, then carbon content of the bath is very high. So, you have to decrease the carbon, that means you have to refine. So, the refining became essential, and the refining of stainless steel essentially consists of carbon and chromium, and to obtain the both carbon and chromium up to the specification. What is the science says? The science says, if you have a melt which contains iron, carbon and chromium, and if you supply oxygen for removal of carbon, if you see the Illingham diagram, you will note that the oxidation of carbon begins only at high temperature. So, unless you have a very high temperature, the carbon oxidation will not proceed. So, let us see now what is the underlying thermodynamics of decarburization of chromium melt. So, thermodynamics of decarburization of chromium melt. What we are doing now? We are trying to arrive the conditions under which carbon oxidation will proceed or chromium oxidation will proceed. So, chromium oxidizes to Cr2O3 or Cr3O4. Now, let us take it, it oxidizes as Cr3O4, and we write down the reaction, say Cr3O4 plus 4C, that is equal to 4CO, the gaseous phase, plus 3 chromium. Now, if you write down the equilibrium constant K, that will be equal to H 3 CO HC and activity of Cr3O4. Remember, again the liquid steel behaves follows Henry's law. So, accordingly we put, for example, certain assumption. Let us take activity of Cr3O4 is equal to 1, H chromium, that is equal to FCr into wet percent chromium, and HC, that is equal to HC into wet percent carbon. So, if we replace HC or SCr and activity Cr3O4 by 1, then we get K, that is equal to FCr W chromium 3 PCO to the power 4 and Fc into wet percent carbon to the power 4, here also Sc to the power 4, and activity of Cr3O4 is equal to 1. Now, say Fc and FCr, they are activity coefficient of carbon and chromium in the melt. Now, this is a very complicated relationship. Now, say Hilty and Cavani, have proposed the following equation. They proposed the following equation: log, say, wet percent chromium in the metal upon wet percent carbon in the metal, that is equal to minus 13800 upon T plus 8.76 minus 0.925 log of PCO. Now, this equation is valid when there is no nickel. T is to be substituted in degree Kelvin. Now, in presence of nickel, the following equation is to be used: log weight percent chromium melt upon weight percent carbon in melt, that is equal to minus 13,800 T plus 4.21 weight percent nickel plus 8.76 minus 0.925 log of PCO. Now, why it is so? So, nickel increases the activity coefficient of carbon. The activity coefficient of carbon in the melt. Now, what we can do now? We utilize these two equations and we can calculate the ratio of percentage chromium upon percentage carbon in the bath as a function of temperature as well as a function of CO, to illustrate what will happen if we increase the temperature or we decrease the partial pressure of carbon monoxide, and this we will be taking in the next lecture.